Hi everyone. So continuing on with chapter 2, we're going to talk just a little bit about atomic structure. We're going to keep it pretty simple. This isn't a physics class, so we really just have to know the basics. So basics of atomic structure, well, atoms are really, really tiny. They're so tiny that we can't really even imagine how tiny they are or put that into perspective. And then we know about the nuclear atom. The protons and neutrons are in the nucleus, and that's almost all of the mass. For all practical purposes, that's all the mass of the atom. And then electrons occupy the space of the atom and very little of the mass. And so we're all hopefully familiar with this from just either common knowledge or previous science classes, if not high school, then middle school. You know about electrons, protons, neutrons, and kind of what the atom looks like, even if we can't picture how small it is. And so this graphic from your book is kind of interesting, where you've got the size of the atom, about this one, 2 times 10 to the minus 8 centimeters. So again, that's a number that doesn't make a whole lot of sense to us. We can't really picture how small that would be. We certainly can't see it. Uh, and so then the idea that the nucleus is 10 to the minus 13th, so that's what, 10 to the 5th difference. So the nucleus is just this tiny little spot in the middle. And your book has some good analogies about, if you had a football field and you'd have this P in the middle of it or something like that. So that's the picture, the atom, just basic atomic structure. And then there's a little bit of history of how they figured this out in this chapter. Um, Not a lot, and I think the history is really interesting, but that's not, you know, that's not what this class is about. We have enough to learn without knowing the names of the people that discovered this and that. Certainly read through that, but we're not going to cover it in any detail. Uh, I am going to just talk briefly, or try to be brief, about this one experiment that was really key in determining the nuclear picture of the atom. And so the reason we'll do that is just because when we talk about the scientific method and I go on my little rant and talk about how science is really done, this is a really good example of it. So, I mean, in this case, they had a hypothesis, right? But the point was trying to disprove their theory in order to gain more evidence for it, right? If you set up experiments that if they turn out a certain way, they'll show that what you were thinking was incorrect, and then they don't turn out that way, that is more evidence towards that your theory of the atom in this case was correct. So they had this idea uh, that the atom was made up of this diffuse positive charge, and then they had already figured out electrons, and the electron charge and stuff, and they could, those cathode ray tubes, if you read that part of the chapter. And so they thought the electrons were these little things kind of just plopped into this diffuse positive charge of the atom. And so that was called the plum pudding model. Now, I don't know what plum pudding is, but anyways, like a pudding with these little spots, and those electrons kind of just mixed throughout it. And the idea of that theory then, or to try and prove it or disprove it, is they thought that if they shot these alpha particles, so the alpha particles are big particles. If you look those up, those are helium atoms. And so you're going to, these different radioactive particles. So if you shoot a beam of alpha particles, these big, heavy particles with a lot of energy through this gold foil. So gold is kind of a really cool metal because pure gold, you can hammer it out, make it really thin. It's really malleable. And so they made this really, really thin sheet of gold. And if their plum pudding model was true, they thought that these alpha particles would go right through it, and some of them would be deflected a little bit by the electrons. And when they actually did the experiment, then they got something totally different than what they expected. So that's cool. That's when breakthroughs happen in science, right? So Rutherford did that experiment of alpha particle shooting it through this gold foil, and some of the particles did what they expected. You know, they went right through or were deflected a little bit, but some of them were deflected a lot, way more than what they thought could happen if they just went by an electron. And some of them actually bounced back. They just were reflected. And there was no way that that could be consistent with the plum pudding model. So Rutherford came up with this nuclear model where you must have this really heavy center, tiny center of the atom, and that when the alpha particles hit that, the nucleus, then they would bounce off. If what they thought of this as, it was so surprising to them that it was like, you know, shooting a big huge cannon through a cotton sheet and watching the cannonball bounce back. I mean, it just completely was different than their expectations. So that's kind of interesting and cool. All right. So what do we need to know about atomic structure? So there's a table like this in your book. Um, this is just my version of that, and let me get something to highlight with here. So we need to know the names of the three particles: electron, proton, neutron. You know, we'll use the symbol E with superscript negative for electron. Proton's actually hydrogen ion, so H plus is a proton or P, and then N for neutron. And you need to know the charges on these. I'm guessing most of you do. Electrons are negatively charged, electricity. Protons are positively charged, and neutrons are neutral. Um, so this is where in class normally I have all these really dumb jokes. I'm not sure they're going to work. So I didn't remind myself to say, oh, a neutron walks into the bar, asks the bartender how much for a beer. For you, no charge. You know, I mean, seriously. Anyway, without telling it in class, I can't hear the groans or get the kind of looks like just get on with it bit. Anyway, so the locate, you need to know the charge on them, and then the location. I won't attempt that again. I wasn't gonna do that actually. That just kind of happened. The location, then electrons outside the nucleus obviously and take up most of the space, and then the protons and neutrons are stuck together in the nucleus. The mass in atomic mass units. So we'll talk about atomic mass units later when we do start to do the mole and all that kind of stuff. But so you don't need to know this mass in atomic mass units, you know, out to 0.00055. Basically, what we'll do is, you know, an electron doesn't really weigh anything. Protons and neutrons weigh about 1. So when you add up the mass of an atom, you know, it comes close to this. And you can't actually add up. We'll talk about this a little bit when we do isotopes and average atomic mass. You can't really just add up the mass of protons and neutrons and electrons to get the mass of the atom anyway because of the nuclear binding energy. And then the mass in grams, that's just there because, you know, these are numbers that we can't really fathom, and just to show us how small, how light the subatomic particles are, 10 to the minus 24th, 10 to the minus 28th. There's no real way to conceptualize that other than that it's incredibly small. So terms of definitions, we need to know these terms. And let's see if I can underline them for us. I don't have a computer with a pen on it, so this is, you know, doesn't work that well with a mouse. So the definitions, I just like to stress it. Atomic number, you need to know what the definition of the atomic number is. It's the number of protons, and that determines what element you have. So the mass number is just you add up number of protons and neutrons, and we call that the mass number. So that's, the mass of each of those is about 1, and so that's why it's the mass number. And then isotopes. So isotopes are different atoms of the same element that have different numbers of neutrons. So they weigh different. They'll still bond in the same way. They can have slightly different chemistry if they're small elements. So there are isotope effects, and you can study different diseases and reactions based on, putting in, say, deuterium instead of hydrogen, or oxygen 18 instead of oxygen 16, and kind of increasing that. So they're kind of cool, but we just need to know that, it's different number of neutrons. And then there's some symbolism for isotopes, the way that we write them. And so this is helium. Helium has a mass number of 4, an atomic number of 2. And based on this, we can figure out all of the particles, right? So a neutral atom of helium, if its atomic number is 2, that means it has 2 protons. To be neutral, it has to have 2 electrons so that the positive and negative charges balance out. And then from the mass number, we can figure out how many neutrons this isotope has. So there's 2 protons, there must be 2 neutrons to add up to 4, right? All right. And we'll do examples of these in another content video where we'll, there's a whole bunch in your homework about figuring out from the isotope symbols how we write them, how many electrons, protons, or neutrons it would have, and stuff like that. And so these symbols for isotopes, I've got carbon up here. And so carbon 12 is most of the carbon. And so when we have carbon with an isotope symbol, we also can just say the element name followed by the mass number. And so we refer to an isotope of carbon that has a mass number of 12 just as carbon 12, or the next one's carbon 13 or carbon 14. It's just a way of talking about it. And really, having the atomic number on there is redundant. Sometimes they'll leave that off. We won't do that in Gen Chem, but we could figure out if we had the symbol carbon and the mass number. Well, we know carbon has an atomic number of 6 from the period. We can look at the periodic table. And so see, that 6 doesn't change. That's what makes it carbon. And then the mass number changes. And so about 99% of carbon is carbon 12, about 1% is carbon 13, and then there's the radioactive carbon 14 that, radioactive means it will decay and give off radiation. And so when it does that, we can measure that. And since organisms take up carbon when they're alive and stop taking up carbon when they're dead, we can use that radioactivity to figure out how old something is. So the half-life, that means the time for half of it to decay, and we'll do that in the second semester when we do kinetics, for carbon 14 is 5,700 years. And so you can use carbon dating to determine how old something is, if it's got carbon in it. Anyway, so the atomic mass unit, then, this is not obviously something you would have to know, but we could use it as a conversion factor. And so 1 AMU, or atomic mass unit, is this 1.66 blah, 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 times 10 to the minus 24th grams. So it's just this, really tiny number of grams, and it's not very convenient to work with numbers times 10 to the minus 24th. So we're going to use, scientists just decide, let's use for convenience, we'll call this the atomic mass unit. And that way, when we look at the masses of atoms, they're numbers we can deal with a little bit easier. And so one atomic mass unit then is defined as exactly 1/12 the mass of a carbon-12 atom. This actually changed historically, I think, a long, long time ago. It was oxygen-16. And this is where doing this on video isn't good, because if I say something wrong in class, I can always, it just goes, it's gone. But that's my memory, memory of, I'm not old enough that it was oxygen-16. But anyway, it's defined that way. And so only for carbon-12 will it be an isotope that has exactly that mass, because otherwise it's going to be slightly off. We don't need to know about nuclear binding energy or anything like that, but you can't just add up those masses. And so carbon-13 will not weigh exactly 13. It'll weigh just slightly different than 13. And carbon-14 will be just slightly different than 14. Be close to 14, but it won't be exactly. Only for carbon-12, and that's where the definition comes from. Anyway, so I'll post some examples so that we can practice writing isotope symbols, and some examples like the homework, so that you're more prepared for the Chapter 2 homework. All right, let me know what you need help with in terms of homework problems, and I'll see you in the next content video. Thanks.